Hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In this particular discussion, I'm going to look at an aspect of conservative forces. Now, in our previous discussion, we had mentioned that basically we can give an element of work given in terms of the force times the distance shown as such. And we had said that in this particular case, we're going to consider the particular displacement from initial position to the final one as the displacement. Now, if we consider an object that is going to move from an initial point to the final point given as x initial to x final, we're going to consider the displacement d given in this particular case from this specific illustration shown as such. Now, there are some special properties which we are going to consider for conservative forces, which are particularly two in nature, whereby we're going to consider the kind of work that is done on a particle that is moving between 2 points. And this is going to be independent of the path taken by that specific, of course, particle. Now, suppose we have a particle that is, of course, this one and this one. And we have this specific particle moving from the initial position, which is going to be given as I or xi to the final position given as xf. So if we consider the path taken as A and B, we're going to see that for a conservative force, what can be identified as a conservative force which is involved in this specific case for the displacement of a particle from a position, its initial position to the final one. We're going to see that the work that's going to be, or the work this specific force is going to do on this particular object moving from this initial to the final position is going to be independent of the path taken by this specific object if we consider 1 and 2. Now, in a second scenario, we're going to see that a second property of this specific conservative force can be explained, whereby we're going to see that the work that is going to be doing in this particular case is by moving an object from this specific point to the last one through a closed path is equivalent to 0. Now, in this case, I'm going to consider this specific illustration, whereby if we have this specific point as an initial point and an object is moving from this particular point using this particular path, and if the final place is still going to be at this point, let's give it as pp, we can give this particular point as a final given as such. So from the relationship, then therefore we can see that point P can be defined as x initial, which is the same as x final given as such. So in this case, if we are trying to consider the element of work, which we said is, of course, a half, we are given this specific element of work as a half. Sorry for that, not half. Basically, this was a product of force times the distance from our first definition. So we can have this one work given as force times the distance given as that, which I explained that basically the distance is going to be the displacement from initial to the final position. So if we multiply the element of work times the displacement from the initial to the final position, we're going to see that if these two values are equivalent, then therefore we're going to have this particular element of work equivalent to 0. So this is going to give us the second characteristic of a conservative force. If the work which is going to be done by this specific force or on the particle that is moving through a closed path is equivalent to 0. Now, in this case, we are going to see that for a closed path, the point of the initial point of a beginning, or the initial point which is a beginning, actually is going to be also identical to the end point, and that's going to define, of course, what we refer to as a closed path. Now, in this specific case, those are the special properties of this specific conservative force, whereby the first one is going to be the work done is independent of the path taken by this specific particle. And then for the second case, we're going to see that for a closed path, of course, the total work which is going to be realized from this specific case is going to be equivalent to 0. And in our, far away from that, in our previous discussion, we had talked about the element of work, especially which involved this specific concept of a potential energy, whereby we said that work can be given in terms of mg y, and of course that one also given in terms of y initial minus mg y final given as such. And we had said that this first aspect of mg is going to depict what we refer to as a force. So therefore, in a sense, it's going to be the force times the displacement, which is from y initial to y final, having factored that this specific element of F still can be defined as such. So we're going to have this mg as a force times the displacement of y initial, y final, given as such. So this was a definition of the weight of an object from our previous discussion. Now we can see that basically this aspect of mg is dependent on the y initial and the y final, but it's going also to be independent of the part that is going to be taken, and therefore we can consider that one to be a conservative force, whereby we're going to see that that one as well can be given in terms of Wg, which is going to be a gravitational, what is referred to as the work done by gravity, which is going to be, of course, a conservative force, as I have said. So we're going to look at other aspect of this specific conservative force, which perhaps can be given in terms of the potential energy, which we had looked at from our previous discussion. Now, in this case, we can consider the work done, which is going to be, of course, equivalent to this change in potential energy. So therefore, we can define work done by conservative force as the change in potential energy. And in this case, we had mentioned that basically we can represent a potential energy in terms of V, so which is going to depict the delta V given as such. So in any case, if I write delta V, that one implies the change in potential energy. So therefore, we can give this one still in a version of work done is equivalent to a potential energy initial minus potential energy final, given in that specific format. So taking into consideration that basically the potential energy is equivalent to V, then therefore we can rewrite this specific perhaps a second equation in terms of V, whereby we are going to have the delta V, which is equivalent to work done by this conservative force, can be given in terms of V initial minus V final is equivalent to the negative value of delta V. So I've explained the implication of this specific value, whereby we are going to see that this is going to be the work done by conservative force, which is going to be equal to the decrease in the potential energy of a system, as we have shown above. And we can evaluate this work done by conservative force as particles move along perhaps x direction or y direction, as we have said, by using this specific concept of an integral, whereby the work done is equivalent to the integral between x initial to x final of this element of a force in the x direction, and of course the displacement in the x direction. So basically this is also going to be, since we had said that this delta V is equivalent to W, this basically is going to be also equivalent to negative delta V, as we have given it in this specific case. Then therefore we are going to be giving this specific format of the work done, which is equivalent to delta V, which is a change in the potential energy from V initial to V final, and which is the negative value of the integral, of course, of from x initial to x final, which of course is equivalent to the forces in the x, of course, direction. So we're going to give this force in x direction in terms of fx, and of course that's going to represent that specific force in the x direction given as such. So from this one, we're going to see that the delta v is going to be a negative value, whereby we're going to consider the fx and dx, which are going to be in the same direction. Now we are going to be finding some location of reference, whereby we can as well regard it to as a reference point for us to identify this aspect of potential energies which are going to be associated with this particular motion which we have, or a particular forces which we have described. In this case, we can identify perhaps xi as our reference point, whereby we're going to measure all the potential energies or the potential these conservative forces from this specific point of energy. Now in this case, from this particular consideration, then therefore we're going to see that if we have established this particular location, we're going to make it a reference point and measure all the potential energy differences with respect to this specific point. Then therefore, if we are going to find the potential energy final with respect to this specific point of x, which we have made as our reference point, can be given as the integral of this specific point from x initial to x final, given as such. And this is going to be, of course, the integral of this specific element of fx given as such plus v, and of course that's going to be vix. So this is basically rewriting this initial, of course, evaluation which we had given as such. Remember, we're going to take this one in terms of if we bring this one on this other side and take this one, of course, they are going to be having to change this specific aspect of the equation. So negating this one, we're going to have this one written in this specific form, whereby we're going to have this point of reference, or the initial point of reference, using this specific aspect of a vi given as such. And as we said, this is going to be the initial point, whereby we're going to have vi taken to be a reference point, and this is going to be having a value of 0, and therefore that's going to assist us in trying to evaluate that change in potential, or the final potential, having taken consideration of that final point given as such. So basically, this is going to be assisting us in trying to evaluate those various aspects of conservative forces, and they're going to assist us in trying to do various evaluations which we are going to come across, especially in our discussions on different aspects of these particular forces. Now in this case, we're going to have this one given as such. All right, just so this is going to be given as f x direction times this. So this is going to be particularly this one given as, so this is going to be an integral given as such. There was a confusion, slight confusion in this particular part, but that's how we're going to evaluate the various conservative forces that we're going to come across. So this was a general description in trying to describe the work that can be done by conservative forces, and how we can relate this specific aspect of our work and the change in potential, which are basically the same, and some of the equation, or the general equation, which we are going to use in trying to do that specific evaluation. So kindly check our description boxes for various links of other videos, and also engage us in the comment section, subscribe, and also ring that notification bell for other updates in sciences and mathematics. So that is it for now, guys. Bye, God bless you. Catch us in our next video.